Hello? Hello? Big room, we don't talk. Any questions from last time? So, this time, I'm going to tell you about a few algorithms, okay? With any luck, I'll tell you about three killer algorithms. I think you are going to like all three, all right? So, they are very different. But maybe we'll stop at two, which is fine too. So, we started talking about modular arithmetic, how to do arithmetic operations, modulo a number. We talked about exponentiation and so on. And you remember, the reason why you are so much interested in that is because of RSA, okay? And RSA. It's the RSA crypto system. Have you taken 70? RSA, the RSA crypto system. It's really it was in 70. So encryption, cryptography, public key cryptography. Okay, RSA. Okay. So the reason why you're interested in modular arithmetic is because it is the engine behind public key cryptography. About RSA. If you think about it, RSA is not exactly an algorithm, okay? It's something much more complex. It's a crypto system, okay? So here's the difference. In an algorithm, you want things to be easy, okay? That's what an algorithm, in other words, we are really trying to, for things to work, okay? To be easy. In a crypto system, like RSA, like public key cryptography, you don't want things to be easy. You want some things to be easy and some things to be hard. You get it? Everybody sees the difference? That's what cryptography is about. You want you to have an easy time encrypting, and the bad guys to have a hard time decrypting. Okay, that's what I'm saying. Is this clear? So, every crypto system you are going to see is based on two things. One that is easy, one that is hard. Okay? What is so clever about RSA is that it is based on two things. That factoring is hard, but primality is easy. And it is this difference that RSA is wedging to work. You get it? Factoring is hard, primality is easy. If I give you a huge number, 100 digits, 1,000 digits, it's extremely hard to find its factors, okay? Have you guys ever factored your social security number? You should. It's, you can do it on the web. There are applets that do that. Okay? So, factoring is hard. What is amazing, what we're going to see today, is that primality is easy. Okay? In other words, if I give you a prime, if I give you a number, you can tell if it's prime or not. All right? And that's very useful for RSA. Why is that? Because in order to build an RSA crypto system, an RSA key, you have to find a couple of primes, right? Remember that? So how do you find primes? There are some things to know. One is that primes are abundant, okay? How many people here have prime social security numbers? Don't laugh. There are 15 people in this room, 16, who have prime social security numbers. How do I know? Because if around the number n, some big number like 10 to the 9, because that's what the social security number is, about 1 in logarithm of n numbers are prime. Am I doing this? It's picking up the my shirt as it. Okay. So. All right. So if you think about it, the logarithm of social security number is about 20. Okay, so 1 in 20 social security numbers are prime. That's why I'm telling you that there are 16 people here who have a prime social security number. Incidentally, if you do have a prime social security number, here's good news. You can tell me so in your maybe you should do it with SID, okay? That's even more secure. Yeah. So you can if your SID is a prime number, you can write it on the first midterm and you get an extra point. I'm serious. We always do this in this class. And those who don't, you will get a valuable lesson for the unfairness inherent in life. Okay, so that's yeah.
So when you say
n is a big number. Okay, so let's say 10 million. Okay, the question is around 10 million. How often am I going to see a prime number? And the answer is 1 every log of 10 million. All right? Which is, I don't know, which is like 10, okay, or 12. Do I make sense? Does this make sense? So this means that prime numbers are abundant, okay? But the question is, how do you find, how can you tell if a number is prime? And that's what we're going to do today. All right. So what's your favorite prime number? Let's say 7, okay? That's a prime number. We know it's prime. We all like and love 7, okay? And we know it. So let's take 7. And we're going to do arithmetic modulo 7 for a while. All right, what is there to know about 7? Let's take a number, 2, and raise it to 6, mod 7. Quick. How much is 2 to the 6th power mod 7? 1. Why is that? Because it's 64, and if you divide by 7, you get 63, 1, right? Okay? 1. All right. All right, that was lucky. How about if we take 3? What is 3 to the 6 mod 7? Wait a minute. You guys have read ahead, or you have done this in you have done this in 70? Fermat theory you have done? Yeah. And primarily you have done? No, okay, cool. All right. So, and the theorem is, all right, so that's Fermat's theorem, that P prime means that for all and okay, that if P is prime, it has this nice property. Take any number, you raise it to P minus 1, you get 1, all right? That's one basic fact. There is another fact, which I'm going to And you have proved this, okay? You know how this works. So here is another fact which I'm not going to prove. That if n is not a prime, then unless n is a ridiculously rare exception called a Carmichael number, okay, what am I going to say? That Fermat's little theorem almost has a converse, okay? Almost has a converse. And there are these little spoilers called Carmichael numbers, okay? That don't let it have a converse. The good news is that Carmichael numbers are incredibly rare, okay? The smallest one is what? I think 456 or something like that. So it's, and then the next one is in the 10,000s, and the next one is in the millions, and maybe there are two more, and people don't know more. Okay, so they're fantastically rare numbers. Okay. Yeah.
I don't really understand. N is not prime.
This sentence does not make sense to you?
N is not prime. I mean, that can be anything.
Right. Okay. So let's see. Let me start again. First of all, I have not finished the sentence. Okay. Okay. All right. So this has two if clauses. Okay. The second clause is masquerading because it's unless. Okay. So it's all right. If it's not a prime, and if it's not a very rare exception, then, okay, okay, okay. For at least half of the A's in the range we have that a to the p minus 1 to the n minus 1 is not 1 mod n. Okay? So, what compare with Fermat's little theorem? This is almost a converse of Fermat's little theorem. It's not a converse for two reasons. One reason is that we would like to say that for all numbers in this range, well, that's not possible. For example, 1, if you raise it to the n minus 1 power, it will give you 1, okay? But it says for at least half of those. The second reason why it's not exactly converse is that there are these extremely rare exceptions that we call Carmichael numbers, okay? And we know, people have studied them and they know that they're extremely rare, okay? So, what is the bottom line? Anybody can see why there is an algorithm hiding behind this theorem, this new theorem? Yeah. Great, exactly. So let me repeat for the mic. Exactly that. If you select randomly numbers in this range, okay? And there was even a discussion how to select random numbers, random integers in particular range on Piazza. Then, and you raise it to n minus 1, if you consistently get 1, then something is fishy and must be a prime. Okay? So let's write the primality algorithm. Primality testing. Given n, repeat 100 times. A random number in the range 1 to n minus 1. If a to the n minus 1 is not 1, return n is not a prime. If, so you guys cannot see this. The last line is here. If, sorry, so you repeat this 100 times, and then that line is return n is probably a prime. In other words, if your n can withstand 100 times the test, okay, then you're done. It's a prime. You can use it for your RSA crypto system, all right? Why? Because the chances are it could be a prime, but the chances are 2 to the minus 1 over 2 to the 100, right? You know, is this probability? Should we be concerned about this probability? Don't be concerned about this probability. Okay? This means this probability is essentially 0. Okay? Let me tell you how small this probability is. Imagine the fastest computer in the world. What is the chance that this computer is going to be destroyed during the execution of one particular instruction by a method? Okay, it's much bigger than 2 to the minus 100. Okay? So, of course, we are engineers. We are responsible people. We want to make our algorithms, our systems to be foolproof, fail-proof, safe, but not better than 2 to the minus 100. Okay, because life is much less certain than this. Yeah.
Is there a fast test for being a Carmichael number?
No. Let's see. I jumped to that. Yes, there is a fast test. There is another probabilistic test for being a Carmichael number. It's a little more complicated than this. So I didn't say it. Yes. So there is a fast test for being a Carmichael number. But I mean, if you do this, okay, and you don't get a prime number, then either you are memorably unlucky, you are unlucky, so you basically fell into a manhole that is 2 to the minus 100, okay, Or you are a famous man. I mean, you're a famous person. You discovered the largest Carmichael number. Okay, so that, you know, the New York Times is going to write about you. Okay, so. And there was another question. Yeah.
How does that probability that you wrote change, like, as you repeat it?
Okay, so why is it 2 to the minus 100? 2 to the minus 100? Because I'm repeating it 100 times. If I repeat it t times, it will be 2 to the minus t, right? Why? Everybody sees that? Because I'm doing n independent trials, right? We are now back in 70 land. The chances of success me being uncover if the impostor who tries to, you know, the non-prime number who tries to be a prime is half. What's the chance that I'm going to fail? Okay? What's the chance that I'm going to keep flipping a coin and coming heads when I'm expecting tails? Okay? 100 times. 2 to the minus 100. Is this clear? Yeah.
Isn't there a mod n after the...
Yes. Yes. Thank you. Yeah.
For those Carmichael numbers, instead of half of them being not equal to 1, how many? 0 or very few?
It can be very few. It can be very few. Yeah. So, right. So, there is a way to get around this. Okay, there is a more elaborate probabilistic test that gets around the Carmichael numbers. There is even the deterministic algorithm now, polynomial time deterministic algorithm for finding if a number is prime. Okay, but I think nothing beats the simplicity and beauty of this very simple idea. Yeah.
Will the Carmichael number satisfy Intractable theorem for all k's in A?
Not all. Not all. No. There are going to be some A's, but we don't quite know how few there can be. Okay? So there is, I'm sorry. What am I saying? Yes. I misspoke. It's really? All right. So it's a little more complicated. That Carmichael numbers masquerade very well as primes, okay? But they are not primes, okay? They have factors. So if you ever step on one of these factors, okay, strange things are going to happen. All right? So, but these, or multiples, okay? So, do you remember what's the it's 456 is the smallest Carmichael number? Yeah, so maybe it's worth, okay. So, 561, okay. 561, it's 311 and 17. 561, makes sense, okay. So that's, I think that's the smallest Carmichael number, is it? So here it's a product of 3 primes. It's 51 times 11, yeah, that's true. So here is what's so odd about this, okay? That if you subtract 1 from these and from these 3 numbers divide this, okay? And that's bad. It's bad because only primes are supposed to have this, okay? Primes have the property, but that if you subtract 1 from the number and 1 from every prime divisor of it, okay? This one divides it, okay? And this is, it turns out that that's what makes Fermat's little theorem work, all right? So in the case of 560, if you try 9, it's not going to give you 1 because it's a multiple of 3. Okay? If you try 33, it's not going to give you 1. Or 34. But all other numbers will give you 1. Okay? Yeah.
You said that like the success failure rate for checking if number if a raised to n minus 1 mod n is 1 half.
Right.
Our theorem says that it's at least 1 half, so could it be the case that sometimes it's more than 1 half?
Yeah, actually, it turns out that more careful analysis gives you, and a slightly different algorithm gives you 3/4. Okay. And usually it is much more. Here is why you should expect it to be 1/2, okay? Imagine that you find 1. One number. A such that A to n minus 1 gives you 1 mod n. Okay? Then it turns out that immediately you get half. Okay? So here is why. Because so imagine that these are all numbers. Between 1 and n minus 1, okay? And divide them into those that are good and those that are bad. Okay? If there is at least one good means like this. Have this property. If you have at least one good, the question is, how many bad numbers can there be? The answer is, at most, half are bad, or all. Okay? If it's not all, then it's at most half. Okay? Here is why. Because imagine I take a bad number, call it b. All right? It has the property that b to the n minus 1 is not 1 mod n. Now multiply b by a. Then again, what is a? A is our good number. It's also 1. It's also not 1. Why? Because this is a to the n minus 1 times b to the n minus 1. A times n minus 1 is 1. Therefore, this is not equal to 1. So the point is that for any b here, all right, this a guy will give us another b somewhere here, okay? So if there is any b, any number here, a1, a2, will give us a corresponding b over there. Therefore, since for any good number, I'm sorry, for any, for any, it's the other way around. For any, what am I saying here? I convinced you that if there is one bad number, so if there is one good number, there must be many of them. And that's the argument. So what am I missing? Anybody can complete it?
Well, the thing is, like, if you have an A and then you say you can get a corresponding A times B, but that A times B might exceed N, right?
Must be?
It might be exceed N, so it's not in that range.
No. You always mean, well, A times B, always we take modulo N. You always take it modulo N. Sorry?
What I'm saying is,
you always go modulo, everything here is modulo N. Okay, I don't always show it, but A times B, I mean modulo N. Okay, you always stay in that range. Yeah.
Since every good A, if you multiply it with B, you're going to get a bad one.
Right?
So for every A, you have a bad B. Or you have a bad number.
Right, but I want the other way around. That for every I want to have more good numbers than. You remember how it goes, Satish? Or Panti? Huh? So you are saying that for every A, so I want to say that if there is one good number, I have at least half. Do I? So what is good and bad, okay? Okay. So, all right. So let's pretend that these 5 minutes never happened, okay? So, you know, so that's yeah. All right. So we were all confused, but you were justified, okay? So, all right. So I'll come back and I'll fix this gap. You want to do it, Satish? Or you want to do it now? Oh my God. Oh yeah, no. We'll fix it next time. It's the subgroup of yeah, but so you know, yeah, but all right. Never mind. So what's the bottom line? That we have a very good algorithm, very nice algorithm for primality. And the amazing thing about this algorithm, that this is something that's going to be coming back again and again in this class, is that it uses randomness and probability to advantage, okay? So this is very common, okay? In algorithms, we often use randomness to advantage, okay? And some of the neatest algorithms that we are going to see use randomness in a very explicit way, in a very deliberate and clever way. All right, and this is, in many ways, the most famous randomized algorithm, and one of the first. And so the next thing I'm going to do is I'm going to talk about something else. I'm going to talk about a particular algorithm, not quite algorithm, data structure, where randomness is not just coincidental, just a feature of the algorithm, but it's the whole point of the algorithm, okay? And can you name it? Hashing, okay? We're going to talk about hashing. Okay? Incidentally, there was a discussion in Piazza. Are there readings assigned for each class? So here's my answer. Strictly speaking, no. Okay? However, we are going to be following for 95% of the class, we are going to be following the book. Okay? And I mean, you should take some advantage of this. Okay? And I'm not going to assign readings, but sort of, you know, if you live through the book, you'll see what I talked about. Okay? And if I may say so, that's a particularly easy book to live through. Okay, so it has no formulas, has no sort of long things and so on. Okay, so do it for every class. Highly recommended. All right, so here is the scenario in which I'm going to introduce hashing. It's the same that's used in the book. What's hashing? Hashing is a data structure that supports some operations. What are these operations? Insert, delete, I guess, and lookup. Okay, if you have a data structure that, how do you call these operations usually? What is a data structure that supports these operations? Sorry? Dictionary? Maybe? Okay. So, here is one scenario in which you are going to use this. So here is a hash table. For hash table, you always have the length of the hash table, which is basically a guesstimate of how big your list is going to be, okay? And imagine that in this particular instance, we have, we know that it's going to be about 250, okay? Just for the sake of argument, just for the sake of example. And basically, what we want to do is we want to map a huge space into this, okay? The huge space we are going to map, actually in this case is something very specific, is IP addresses, okay? So imagine the following, that for some application, we always must keep a list of about 200, 230, 250, who knows, about that, around that number, IP addresses, okay? And we have to make very, very quick lookup and insert, delete, and so on, okay? But we know that the size will never exceed around 250 IP addresses ever, okay? IP addresses, you realize, are the things like okay? They are, how many are they? They are about 2 to the 32, right? Which is more than 4 billion, okay? Almost enough for every person to have its own, right, on Earth, their own. So, and we want basically to have a mapping, it's this hash function h, that maps any address to the hash table, okay? And the question is, we want to find a good hash function. All right? And the question is, what does good mean? So in designing a hash function, you are conflicted between two goals, okay? You want this function to be random so that it spreads equally everything to the hash, to the buckets in the hash table. And you also want it to be consistent, to be a function, right? So that if you hash the same thing twice, you go to the same bucket. Otherwise, you're in trouble. Is it clear? So this is basically the conflict that in which you find yourselves when you want to design a good hash function. All right? Sorry? You also want it to be easy to compute. Yes, exactly. Of course, you want it to be easy to compute. Yes, right. So, how do you resolve this, okay? First of all, what are we looking for? What is a good hash function, okay? For example, if is this hash function where you take the last this 256, that's almost good, okay? So you could just take the last 8 bits and call it hash value. Is this good? It's who knows? Probably not, okay? If the small numbers are preferred, then you are going to have a very crowded hash table, okay? It's going to be terrible. How about if you take this? That's even worse, right? I mean, no, because I mean, all of South Carolina has one or something. I mean, so you know, so what if all your customers come from Asia or something? Okay, it's going to be a terrible idea. Okay. So these are bad hash functions. In some sense, there is no such thing as a good hash function. Okay, all hash functions are bad. Okay, think about it. That no matter which hash function you choose, okay, there is going to be an incredible number of IP addresses that map to the same bucket. Okay, if you get a lot of these, you are in trouble. So one thing to remember is that strictly speaking, there is no such thing as a good H. One that is guaranteed for for any list of IP addresses to give you a nice spread. Okay, that's impossible, completely impossible. So here's an idea. So I'm going to propose a particular family of hash functions, not just a family of hash functions. Let's call it H. And every element of H is going to be the following. So imagine that H every element of H has the following form. H of, let's call it X, Y, Z, W. You get it? These are the four fields of the IP addresses. It's going to be a number times X plus another number times Y plus another number Z plus another number W. Of course, mod 256. Actually, let's make it mod 257, not 56. Why did I say 257? Sorry? It's a prime number. Okay? You see what I'm saying? Here is one way to get, I think, a fine hash function. You pick a number A, modulo 257, let's say 87, a number B, 201, a number C, a number D, and then you do 4 multiplications and 3 additions and 1 modulo operation, and you have your value. Okay, that's quite fast. All right. Is this a good hash function? Incidentally, the hash functions I told you before, the one that picks the last group or the first group, they are special cases of this. Okay, just take 1000 or 0001. Okay, so this is sort of a generalization of these bad ideas. Okay. So what can I say about this? Is it a good hash function? I don't know. As I told you, there is no such thing as a good hash function. but I can tell you something about this family of functions. Now, this family of functions is good. Okay? He has the following property. For any x, y, z, w different from, for any two different, IP addresses, the probability if I draw A, B, C, D at random, the probability that h of x, y, z, w is equal to the h of x prime, y prime, z prime, w prime, this probability is small. Okay? You see what I'm saying? Suppose that I draw my A, B, C, Ds at random. This family of hash function H has this property. Suppose that every morning I draw my A, B, C, Ds at random, okay? And then I create my hash table. What I'm claiming is that the probability that the two different IP addresses, any two different IP addresses, I pick any two different IP addresses, the probability that they hash to the same value is what? Is very small. How small can it be? Can it be 0? What's the smallest conceivable value that it can be? 1 over? Right. N is the size of my hash table. That's the smallest possible value that it can be, right? Yeah. Sorry?
The probability
Yeah.
that has to be equal has to be slightly greater than 1 over 57. Because there's a non-zero probability, you pick A equals B equals C equals D equals 0.
True? Well, if, what I'm saying is this, that if it so happens that A equals B equals C equals D equals 0, okay? What's the probability of that? That's 1 over 257 to the 4th power. So that's this is one of the counterexamples. There are many counterexamples. My point is that they are very rare. Okay, if you get 1,000 hash functions, only 4 of them will have the property that they map these two particular IP addresses to the same thing. Okay, you picked out one. Okay, but there are more. Okay, yeah. There was another question. Okay, the same question.
No. So it says h of x dot y dot z dot. What exactly does that mean?
It means the following, that we have, that what I have proposed here is a particular way to take any IP address and get a number out of it between 0 and 256. Right? So that's what the h is.
It becomes a number between 0 and 2.
Right.
Then h of x prime dot y prime.
Is another one. I apply h is this function. I define it. Here's the definition of h. When I say h here, I mean this. Right? And the point is that if you give me two different IP addresses, and then I'm allowed to draw my ABCDs, it's very tiny probability that are going to be in the same okay. So, in other words, this family of hash functions, it has some good functions and some bad functions. Okay, all families of hash functions have this. All right, but the point is that it's a good family of hash functions because, on the average, it has a very small probability of collision if you take any two elements in the domain. Okay, is it clear? So, let's see why is this so. Okay, it's a cute little argument. Okay. Any questions? Any more questions? Yeah. Excuse me. Why you chose a prime number? Excellent question. Give me 6 minutes. Okay. Yeah. How do I get? Sorry? This probability? Okay, excellent. That's a very good question. The low, that's why, yeah, okay. Okay?
When you wrote there 257 and n, is that a product or is that?
No. It's 5257 is n. Is the size of my hash table. Okay. So what I'm saying is that when I'm going to come back and say what have we learned, we didn't learn 257. We learned n. Okay. That's my point. Okay? So, what I'm going to do now is convince you that this is so, that this is the case. All right? Okay. So, here is the... We know that these two guys are different. Okay? We know that x, y, z, w is different from x prime, y prime, z prime, w prime. So without loss of generality, assume that w is different from w prime. Since these two are different, either this is going to be different, or these two are going to be different, or these two are going to be different, or these are going to be different. So without loss of generality, let's say that the last ones are different, okay? Could be that all of them are different, but let's insist that the last one is different, okay? No, nothing up my sleeve here, right? So you want to know what's the probability that ax plus by plus cz plus dw is the same as ax prime plus by prime plus cz prime plus dw prime mod n, mod 257. Sorry? I didn't hear you. I didn't understand you. Why am I writing this, you are saying?
You're assuming that x, y, z, and x prime, y prime, z prime are the same, right?
No.
But you were saying the only thing is w is not equal to w.
I know that at least w is. They could be the same. They're probably different. Okay? What I've written here is that w is different from w prime. No. Okay, I'm starting again. My assumption is that these two IP addresses are different, okay? So what does it mean that they are different? It means that there is at least one field which is different, okay? At least one. Let's say it's the last one. That's all I'm saying. Suppose it's the last one, okay? Good. And now let's do the experiment, okay? We are drawing the A, the B, and C, and the D, okay? And we draw the A, it's something. We draw the B, it's something else. We draw the C, it's something else. And then we stop and think before drawing the D. All right? What's the chance that this happens? Okay? Now we know all these 8 numbers plus these 3. You get it? This equation is the same as saying that D times W prime minus W is equal to A times X minus X prime plus B times Y minus Y prime plus C Z minus Z prime plus D W minus W. Sorry, that's it. Mod 257. Just algebra, right? My whole point is that this now is a number, okay? Call it A, capital A. Because we know all these numbers, okay? We can calculate it. Is everybody with me? No. Okay. We started, cool, thanks. We started by knowing all the x's and the y's and the z's and the primes, okay? Now we also know the A, B, and C. Therefore, the right-hand side is known. It's a known number. Like 51. Let's call it A. Let's not call it 51. Let's call it A.
Why is the right-hand side a known number?
Because we know A, B, C, X, X prime, Y, Y prime, W, Z, Z prime. No, because we have not yet drawn D. Okay? Okay? So I hope there is suspense in the room, okay? I have drawn A, B, C, and D, and now I'm about to draw D, okay? What are the chances of failing? How am I going to fail? How am I going to make these things equal? What is the chances of these two being equal? What must happen for this to be equal? D must be equal to what? To A times W prime minus W inverse, mod 257. And thank you very much. This is why I chose 257 to be a prime, okay? So the only way that my whole plot can fail and my hash function will embarrass me and will make these two things equal is if D is this particular number, okay? And what is the chance that D is this particular number? It's 1 over 257. So that's the proof. I didn't write proof because I would intimidate you, okay? So, you know, it's just a clever argument, right? Do I make sense? Yeah.
When you went over the hash table, you've chosen that the hash table was going to be only ranked 250?
In the beginning.
In the beginning, yeah.
Right, yes.
In between 250 and 350, so it doesn't matter when you
Exactly. I mean, so it's right. So let's see. Let's look back and see what we have done, okay? We have, as is usual with hash tables, we have the task of mapping a huge, humongous space of keys into nicknames, okay? Into a small key space, a small bucket space, all right? Big N into small n, okay? That's looking back here. big N into small n, okay? How do we do it? First of all, we pick an n which is large enough and prime, okay? Large enough, in this application, we said it's going to be at least 250, okay? We pick the next prime after 250, okay? Everybody with me? Then, which is 257, I believe. Then what do? We rewrite this number n, which is the whole key space. We write it as a small m little n, k raised to the kth power. This is a prime. We find a power k such that it covers our huge space. Now, every element of our huge key space can be written as a k-tuple of integers, right? Each of which is less than or equal to n. Everybody sees that? Okay. So imagine now that we write every key in base n. Okay? Since there are at most n to the k keys, I will only need k digits, where every digit is n, to write them, okay? That's why here it was 4.
Why are there at most n to the k keys?
Because I choose k so that there are most n to the k keys. I choose k big enough.
Why do we care about n to the k? Why do we want it to be at most n to the k?
Okay, because I want every key not to be a flat number, but a k-tuple of numbers, each one of them between 1 and n, 0 and n. Like we had here. Not clear. Anybody else wants to ask this question? Sorry, yes, it's not going to be exactly 1 to 1, right? Because we are going to have. Okay, we have this number n. Okay, it's the basis of our. It's the size of our hash table. Okay, obviously our key space is much bigger than that. Okay, I pick a k so that n to the k is bigger than my key space. In this case, it goes 4. Now, every key I can write in n array, little n, base n.
Say that one more time.
Every key I can write it in the system base n, like base 10, base 2, base 3, base n, okay? So it's going to have k digits. Each one of them are going to be between 0 and n. Yeah, I think you should, yeah. Anybody wants to? Yes, please. So this is exactly this is in the book. It went over too fast. Do you have a question? Sorry? Okay. Okay. No, it's easy to review. It's 3 pages in the book. Yeah.
I don't understand the part where is D equals A, the last part.
This one. This part. Okay. So visualize what happened, okay? First of all, they gave us two keys, two IP addresses, and they asked us to find a hash function that's good for them, okay? And we say, okay, we'll pick one at random, and the argument is that this random function, with very high probability, will not collide them, will not make them collide, okay? In other words, the probability that they collide is going to be 1 over 257, all right? So here is how we argue this. We have these x and x prime and y prime and so on. These are known numbers, all right? We draw A, we draw B, we draw C. What is A, B, and C? Are the coefficients by which we multiply x, y, and z in order to get our hash function. Okay? Now, all of these numbers, except for D, are known. And the equation that these two are the same becomes exactly this. In other words, the only way for these two IP addresses to collide by my randomly selected function is if in the last act of the drama, when I draw D, this D happens to be equal to that. But that's one particular number. So D has to be that number for me to fail, for this to be equal. Is it okay? All right. So, cool. I promise that I will give you a third algorithm, so let's at least start talking about it, all right? There is this mathematician, 19th century mathematician. His name was Carl Friedrich Gauss, okay? Okay, you cannot live without hearing his name, okay? So he's very, very famous. Probably some people would say he's the greatest mathematician who ever lived. So when he was in first grade, he calculated how much is 1 plus 2 plus 3 plus 4 plus 100. Okay, that's a famous story. Okay, which is what's the answer? 50-50, exactly. Yeah, right. Yeah, so that's all right. Cool. When he was 18, he already knew about complex numbers. Okay, remember complex numbers? Yeah. So, and he was interested in multiplying complex numbers. And you know what it is. And in order to compute this complex number from these two complex numbers, you need how many multiplications? Count them. 1, 2, 3, 4, okay? And Gauss thought for a while and said, I hate multiplications, okay? I want to get rid of, can I do it in 3 multiplications? Is it possible to do this in 3 multiplications? What do you think? Okay, obviously not, okay? Well, Gauss found a way. Hey. AC minus BD, yes, right, yeah. And this is AD minus BC, right, thanks, yeah. Okay? All right, so this is how you, this is the formula for multiplying complex numbers. So Gauss asked himself, how can I do it with fewer multiplications, okay? And there is a way. You want to see? So here is a way to do it. You calculate AC, you calculate BD, and then you calculate A plus B times C plus D. And now you are done, because BC plus AD, which is the thing you are missing, the imaginary term, is A plus B times C plus D minus AC minus BD. That's young Gauss's method of multiplying complex numbers, okay? Get it? You see what's happening? By doing this nonsensical multiplication that doesn't seem to be needed, okay, you save one multiplication. You see why? Because now you have AC, you have BD, you need both of those, and then the imaginary term, BC plus AD, you can get it by two subtractions, okay? So instead of doing, as everybody else, 4 multiplications and 2 additions, he did 3 multiplications and 1, 2, I guess 3, 4 additions. So he traded 1 multiplication for 3 additions. So depending on how big your numbers are and how much you hate multiplication, it was a good deal for him, all right? In any event, it's a clever thing, okay? But of course, you look at it and you say, what an incredible waste of ingenuity, of cleverness, right? you sit all morning and you come up with this and you feel satisfied with yourself. And what you have done is you have traded one, it makes little sense. What's my point? My point is that in this class, we are going to be analyzing recursive algorithms, okay? And if you do something as silly as this in a recursive algorithm, suddenly the recursive algorithm speeds up incredibly. You can see why? Because recursive algorithms have a way of amplifying tremendously, exponentially, any cleverness. Okay, so if you do this in the body of a recursive algorithm, you win. If you do this when you do your math homework, you lose, okay? Yeah.
I can understand why computer scientists would like this formula for multiplying numbers, but what drove Gauss to say, hey, I want like to move more?
Probably he was working on something that had like 6-digit numbers, and he was sick and tired of doing multiplications. Okay, that's because back then you have to do everything by hand, right? I mean, also. Okay, so here is what happened. That was beginning of the 19th century, okay, 1810. 150 years later, 2 people in Russia, 2 mathematicians in Russia, remembered Gauss's trick and used it to find a recursive algorithm that multiplies any number, 2 numbers, okay, any 2 integers, in less than n squared time. Okay? And it's exactly the same trick. Let me tell you how this goes. What's a recursive way of multiplying numbers? Suppose that you have 2 huge numbers, okay? N bits. And we want to multiply them. $100 bits. Big bother, okay? How about if you try to do it recursively? You subdivide them into 2 smaller numbers. Let's call it x left and x right, and y left and y right. And now you multiply. And here is how the math goes, and it's not very hard to see. You have to multiply x times y, right? No bonds, no nothing. That's a real ordinary multiplication. It is the same as x left times 2 to the n over 2 plus x right times y left 2 to the n over 2 plus y right, which of course is x left, y left 2 to the n plus x left, y right plus x right, y left 2 to the n over 2 plus x right, y right. Everybody agrees? And now you can do recursive call. You can write this is a recursive algorithm, okay? You say, if they have only one bit, just do it, okay? If they have more bits, divide them into 2 and do this. Multiply this, multiply this, multiply this, multiply this. And you are almost done now, because you only have to do additions, which are easy, and multiplications by powers of 2. Remember, multiplications of powers of 2 are not real multiplications, right? They cost nothing. You just shift, they're very easy. So, is this a nice observation? You can do recursive multiplication. And at the beginning of the next lecture, we are going to analyze this algorithm, and guess what we are going to find? It's how many steps does it take? It takes n squared. Okay, so we are back to square one. There was a question. Not at all, yeah. All right, so see you Tuesday.